Welcome back to the General Chemistry Fundamentals series. In this video, we're going to talk about molecular geometry and VSEPR theory. Why is it important for the MCAT, and what do these terms mean? When you think of the word geometry, it might remind you of math class back in high school, but the main thing that we're focused on here is shape. The reason we care about a molecule's shape is because it helps us determine the reactivity it might have, the polarity that will exist within the molecule, and the intermolecular forces that will arise between the molecules. All of this becomes critical to understand when we're discussing chemical reactions, especially in organic chemistry. This is going to be very important for understanding nonpolar versus polar molecules overall, not just the intramolecular bonding, but what is the overall net dipole moment of the molecule. We will talk far more about this later. And what are the possible intermolecular forces or interactions that will occur? Those will govern the solid, liquid, and gas phases and physical properties. So what in the world does VSEPR mean? And who knows how to actually pronounce this? That's just the easiest way. But it stands for Valence Shell Electron Pair Repulsion. So valence shell meaning the outermost electrons, we've discussed this before. Electron pair meaning a pair of electrons. Could be a lone pair or a bond. We'll talk about that. And there's repulsion because they all have negative charge. They don't like each other. Coulomb's law tells us that negative charges or like charges will repel each other. How much they repel each other depends on the magnitude of the charge and the distance between the charges. That will determine the force. Now, I'd like to differentiate very clearly between electron geometry and molecular geometry. With electron geometry, we're not really differentiating between lone pairs of electrons or bonded pairs of electrons. When we're looking at the electron geometry, we treat it all as the same. And what you need to know is that the pairs of electrons that exist outside of the central atom are all going to try to be equally distant to one another. They want to space out so that they all have as much space as possible. Now, the question is, how much space is there? Well, if you remember something about circles, circles have 360 degrees. If we think about the space outside of the central atom, there is a 360-degree spherical possibility for electrons to exist in. If you look at all of these spatial arrangements, you'll notice that if there are two regions of high electron density, then they will separate into 180 degrees. So that's 360 divided by 2. Three regions of high electron density, it'll split into 120 degrees divided by 3. But then once we start to get into the 5 and 6 regions of electron density, it has to split itself slightly differently, and you can see those angles. So with trigonal bipyramidal, you can see that there are angles of 90 degrees between what's known as the axial and the equatorial electrons. So they're perpendicular. But all of the equatorial pairs, which go along the equator of the central atom, have 120 degrees bond angle between them because they're all split into 3. So 360 divided by 3 is 120 degrees again. So starting with two regions of high electron density, if there are two things, whether it's lone pairs or bonds, around a central atom, it's known as linear. If there are 3 electron regions, it's known as trigonal planar, all of the 3 being in the same plane. If there are 4 regions, it's tetrahedral. If there are 5 regions, it's trigonal bipyramidal, as we just talked about. And if there are 6 regions, it's known as octahedral. All of the angles are 90 degrees. So here we have a good reminder that the lone pairs are going to have more repulsion than the bonding pairs of electrons. The reason for this is because the lone pairs take up more space. Since they're not part of a bond, they have a little bit of more room that they like to take up, and therefore lone pair repulsion will be more than lone pair bonding pair, will be greater than bonding pair repulsion, and we'll see this with the bond distances and the bond angles as we go into the molecular geometries. So all in all, the lone pairs will have more repulsion than a triple bond and more than a double bond, which has more than a single bond. If we look at our first molecular geometry here, the first one I want to go over is linear, and carbon dioxide is a great example for linear for a multitude of reasons. So carbon dioxide is a molecule that's created from carbon as the central atom, which has no lone pairs on it. All 4 of its valence electrons are being used in the double bonds that surround it. There are two oxygens, and the bond angle between the double bonds is 180 degrees because the double bonds want to orient themselves as far away from each other as possible. The interesting note I'd like to make about carbon dioxide is that the carbon-oxygen double bonds are polar. There is a net dipole moment moving towards the oxygens on both sides. But the lesson we're going to learn here, which goes into polarity, is that if the dipole moments are 180 degrees apart, they technically cancel each other out. So what we're going to notice is that when the molecule is symmetrical as such, and the dipole moments cancel out like we just showed, the molecule is considered net nonpolar. Even though each of these bonds are polar. The next molecular geometry I'd like to go over also does not have any lone pairs around the central atom. In this case, the example that we used is formaldehyde. You've probably heard of formaldehyde before. It's a very common preservative that we use. The bond angle in a trigonal planar molecule with three single bonds would be 120 degrees. If you apply the concept that we had mentioned before, there is more repulsion between double bonds and other types of bonds than there are between single bonds. Therefore, the bond angle between these single bonds in formaldehyde will be 118 degrees. And the reason this occurs is because the repulsion between the single bond and the double bond on both sides will likely have a bond angle slightly larger than 120 degrees, maybe 121. Therefore, the bond angle between the single bonds compensates by being slightly smaller than 120 degrees. Now I'm going to start going into types of molecular geometries, some of which have lone pairs surrounding the central atom. The effect of this is significant because it forces the bonded electrons to move in such a way that the dipole moments might not exactly cancel out, like we saw with carbon dioxide. So in this picture, you can see that the dipoles between the hydrogen and the oxygens are not 180 degrees apart. They're about 104 to 105 degrees apart. This forces the water molecule to take what's known as a bent shape. And this is mainly because of the lone pairs that exist on oxygen. So we're going to look at a table later describing all of the molecular geometries. I'm just going in order for now. But the main thing I want you to take away from this is that there's a difference between electron geometry and molecular geometry. In this scenario, what you're going to see is that there are how many electron regions surrounding the central atom? The answer is 4. So if you'd like to take a guess, take a moment to figure out what electron geometry this would be. If you said tetrahedral, then you'd be correct, because there are 4 electron regions surrounding the central atom. But the molecular geometry would be considered bent. If we move on here to tetrahedral, this is very, very common when you see carbon with 4 bonds around it. You'll also see plenty of tetrahedral intermediates in organic chemistry reactions, especially in nucleophilic reactions. And so that 360-degree sphere is going to have the electrons arrange themselves in such a way that they end up having a 109.5-degree bond angle between each of them. Although 109.5 does not divide into 360 degrees perfectly, this happens to be the angle at which there is the least repulsion and the least resistance between each other. This molecular geometry here is called trigonal pyramidal, which is very common for ammonia, which has a molecular formula of NH3. And the reason it forms a trigonal pyramidal molecular geometry, even though it has an electron geometry of tetrahedral, when we consider the lone pair, the lone pair takes up more space than the single bonded hydrogens do, and therefore there's more repulsion coming from the lone pair. Due to that, the 3 bonds to hydrogen are going to move downward and form the basis of what's essentially a pyramid with a triangular base. That's why this is called trigonal pyramidal. Also, this causes the net dipole to not cancel out as it would with tetrahedral, and therefore ammonia is a classic example of a polar molecule with a trigonal pyramidal molecular geometry. Now we're moving up to having 5 groups surrounding the phosphorus. So in this case, The phosphorus in the middle of PCl5, which is going to be phosphorus pentachloride, is going to have three chlorines in the equatorial position, which means that they have a bond angle of 120 degrees relative to each other, and two chlorines in the axial position, which will form a 90-degree angle with the equatorial atoms. As you can see, phosphorus has no lone pairs. Also, the fact that phosphorus can form this means that it has an expanded octet. You're going to notice for the molecules that have trigonal bipyramidal electron or molecular geometry, as well as things that have octahedral electron geometry, are going to be from central atoms that can form expanded octets. It will be the only way to have this case. And yes, in terms of electron and molecular geometry, if we have a central atom that has six bonds surrounding it and no lone pairs, it will be octahedral for both. All of the bond angles, axial and equatorial, will be 90 degrees respective to one another. Sulfur hexafluoride is a classic example of this. Another thing to keep in mind is that trigonal bipyramidal and octahedral molecular geometries are rare. So you don't have to worry too much about seeing these, but I want you to recognize them. This table depicts the electron geometries if you look when there's zero lone pairs in the first column, and then all of the different molecular geometries that you can expect when there are lone pairs. Please pay attention to the bond angles. Notice when the bond angle is equal to 120 or 180 or 109.5 approximately, or 90 degrees, right? And also notice when the bond angles are less than that. It's usually going to be because there's a lone pair that's taking up more space than the bonds. I'm going to move into some of the less seen or less common molecular geometries. This one's going to be seesaw. As you can see, there are four bonded atoms outside of the sulfur and one lone pair. That lone pair on the top is going to push down on all of the other bonds. This is going to cause the seesaw molecular geometry. So therefore, when there's four bonded atoms and one lone pair, we're going to get the seesaw molecular geometry. The next example is T-shaped. So this would also fall under trigonal bipyramidal electron geometry, but has a molecular geometry of T-shaped, and it ends up looking like a T. The reason being there are two lone pairs on the central atom, as you can see depicted by these yellow balls. Once we move to square pyramidal, we're no longer in trigonal bipyramidal electron geometry. We've crossed over into octahedral electron geometry because there are six electron regions. However, there are only five bonds and one lone pair. That one lone pair is going to push four of the bonds into the same equatorial plane, which is going to look essentially like a square. And then because one of the bonds, one of the atoms gets pushed up into the axial plane, this is going to form what's called square pyramidal. So it means that it has a square base and there is one atom up top to which it could form a pyramid. The bond angle between the square equatorially and the axial bond is not going to be exactly 90 degrees, most likely a little bit less than 90 degrees because, as we said, the lone pair has more repulsive force than the bonds do. In the square planar molecular geometry, we're still dealing with six groups. We're still within the octahedral electron geometry, but the difference is instead of having one lone pair, as square pyramidal did, there are two lone pairs in square planar. So as we said, the equatorial bonds are going to align in the same plane, so it's essentially a flat molecule. The reason it's flat is because the lone pair on the top and the lone pair on the bottom, which want to be as far away from each other as possible, are going to keep that square plane. Therefore, if you see anything that says square in it, it's probably from an octahedral electron geometry. In this case, it's square planar. The fact that noble gases like xenon can form these types of molecules is very interesting. It's not something that you would typically expect, but the fact that xenon has 8 electrons in its valence shell already and then able to form this expanded octet allows it to form these types of molecules. And last but not least, we come right back to linear, but instead of having a linear molecule like carbon dioxide, where carbon had no lone pairs and we had two double bonds, we have a situation where we have xenon again, And instead of having an octahedral electron geometry, it has a trigonal bipyramidal electron geometry, which means that xenon can have either 5 electron regions or 6 electron regions, depending on the molecule that it forms. And in this case, we have 3 lone pairs and 2 bonds. So that's why I wrote trigonal bipyramidal next to it to represent its electron geometry. But molecularly, it appears to be linear because the 3 lone pairs are going to be able to force the 2 bonds to be 180 degrees apart. So in this case, xenon difluoride is going to be linear. I hope this video was helpful with introducing the concepts of electron, molecular geometry, and VSEPR theory. Please keep in mind the negatively charged electrons are repelling each other. If they're located in a lone pair, they repel more than the bond. The triple bonds repel more than the double bonds, and the double bonds repel more than the single bonds because of the number of electrons included in each type of bond. Thank you for watching, and hopefully see you soon.